So many of you probably know what composites are, but let's just define it again. And we are talking about advanced composites um, with the focus of aerospace advanced composites. These are composites that are made using made using two distinct types of submaterials. One is typically an advanced type fiber, such as carbon fiber or glass fiber. And these are embedded in glue type materials, such as epoxy, which is typically the weaker components. So the glue is the weaker components, and the reinforcement, the strength, and the stiffness comes from the fibers. And there are many applications of these materials in aerospace, but the way we design these materials and the way we implement them in large aerospace parts is quite different than traditional metallic materials, and hence the need to have these courses. So let's just start talking about some of these differences. So FAA has identified 10 technical characteristics of composites. And this is a list that has been published by them. So we're going to go through them. And the aim here is to draw your attention to the differences or the specific characteristics of this material, which is very different than other types of materials. First of all, when we are making an aerospace composite part, we start with raw material. These are quite formable materials at the beginning when they're in an uncured state. You have to, we're talking about, let's say for this course, you're talking about thermosets such as epoxy composites. So you have to store them in freezer and at very low temperatures. Then you have to use them to lay down your laminates. You vacuum bag them, you place them inside autoclave, you cure them, and then you have your final shape and geometry. So unlike other types of material like metals, you're creating the structure to net shape. So you start with soft material from the beginning, and then at the end you have a complex, large, solid structure. So in metals, for example, you have sheets and you form the sheets into different shapes, and then you have many components that you have to basically do assembly with them. Here you have consolidation of the number of parts. You have much less in terms of number of parts, but the challenges are different. So since you are creating the structure with this specific steps of manufacturing, you're building in a lot of history of manufacturing into the part. You're building in a lot of variability that might comes from how you, for example, stored your material in the freezer. So every step, there are some uncertainties and there are some variations, some in your control, some outside of your control. And you're baking all of those into your structure. So the way you're manufacturing, the way you're storing your material has a huge impact on the final end part properties. The way you are machining your structure has a very important effect on the end part properties. So the way we describe this is that the material variabilities and the process variabilities affect the material properties. Two is that we call composites notch sensitive. What do I mean by notch sensitive? If you have a coupon, let's say it's tensile coupon, and you cut a hole in it or you put a sharp notch in it, the response of the material under failure changes significantly. Let's do a comparison. You have, let's say, this sheets with the hole in the middle of them. We call them open hole tensile samples. And let's say you're making them out of metals and you're making them out of composites. And then you test them. You measure the strength as you're increasing the size of the hole. So every test you do, the next test you're increasing the size of the hole slightly. And then you plot them in this graph. On the x-axis is the hole diameter, and the y-axis is the normalized strength to the unnotched strength. So as you increase the size of the hole, the strength drops. That's understandable. In metals, we can predict that quite effectively. Under a static load, you're not talking about cyclic load. The strength drops because you're removing part of the material as you increase the size of the hole. So the strength drops. and it's understandable, but you can predict that. But when you talk about composite, the strength drops a lot more than metals, and typically in a way that we cannot predict it. So the effect of the notch is a lot more significant in composite. Also, if you test them in tension versus compression, you will get totally different responses, which again is very difficult for us to estimate. Um, in in metals, typically we don't pay attention if there is a hole and we're talking about static loads. Where we have to pay attention is that if we have fatigue load, which means that we have cyclic loads, and if you have a notch, cyclic load, and if you have a notch or a hole, at the edge of the hole, you have a stress concentration, and that becomes the point that fatigue crack starts growing. So you have to pay attention to that. In composites, fatigue is not as important as metals, but under static load, this is where it becomes quite critical. So static strength changes in an unpredictable manner. So that's what we call composites notch sensitive. Three, out-of-plane loads have a huge impact on composites. If fatigue is something you have to pay attention for metals, out-of-plane loads is something you have to pay attention for composites. So imagine you have a plate and you have a impact, which is vertical, perpendicular to the surface of that plate. That load becomes quite difficult for your material to handle. The reason is that you typically have layers of composites, and they are held together by these weak bonds. In the case of epoxy, these are like basically bonds that are formed during curing between the layers. If there's impact, it's easy to separate the bonds and create a defect known as damage called delamination. So here on the right, there are three cases that same size and thickness of the panel is taken, and then you're dropping a load onto them from different heights. That changes the energy of the impact. The first one has an energy of 5 joules, the second one 15 joules, and third one 30 joules. And you're looking at the front and back of the panel that the impact has happened. If you have only 5 joules, which is a very small amount of load, it's equivalent of having like a pound, almost a pound of mass, drop it from like 1 meter onto the surface of composites. You can see that there's not much effect on the front face of the laminate, but if you look at the back side, sorry, the both front and back side, there is not much hint. But if you do see a scan, which is ultrasound, which looks at the bonds between the layers, you get some hints of delamination. If you start increasing the energy of impact, you start seeing more effect on both front and back side. But delamination is typically much, much larger than what you can see on the surface. So you might have a case that front and back of the panel looks perfectly clear, but you have already delaminated the material. So that has to be considered when you are designing the material. Four is that unlike metals, these materials are anisotropic. So if metals are isotropic, which means that in every direction their properties are the same, composites are typically, we call them orthotropic. So if you take a lamina, in this case, where you have fibers that are parallel in direction one, and let's say it's a thin lamina, so you have direction one where there are fibers, direction two is perpendicular to fibers, and direction three is out of plane. Modulus in direction one is much larger than modulus in direction two and three. Hence, you have to measure the modulus in all three directions when you are actually characterizing these materials. Poisson's ratio is not the same as metals that you have one Poisson ratio value. If you stretch direction one, direction two and direction three, they're going to shrink due to Poisson's effect. The same with if you stretch direction two, direction one and direction three is going to shrink, and the same with direction three. But the ratio of these changes are different. So you end up measuring three different ratios or three different Poisson's ratios. The shear modulus on different directions is very different. If you take direction one and two and want to apply shear load, it resists that, but it has a specific stiffness to resist that deformation. We call that G12. If now you take direction 2 and 3, so it is through the thickness and try to shear that direction, it shows a different value, and the other direction as well. So there are actually 3 different shear modulus that represent the stiffness of the material to resist deformation under shear loads. So you end up having 9 different properties that you have to measure for one single laminate. There are other aspects that would affect this, such as environmental factor, processing factors, which we are not even discussing here. But this is one main difference. If for metals, you only have to measure 2 properties, one elastic Young's modulus and one Poisson ratio. Here you have to measure at least 9 properties. 5, composites are dimensionally stable in plane, which means that if you increase the temperature, given that you have fibers in plane, and typically fibers are placed in different directions, fibers have almost a coefficient of thermal expansion of 0. So when you increase the temperature, the laminate doesn't deform in direction 1 and 2. It would deform through thickness when there is no fiber in that direction. But in plane is quite stable. So imagine you have steel or aluminum that is part that is glued to a composite part, and you increase the temperature. Let's say environmental factor, the temperature goes up, or you have freezing temperature goes down. The metallic part shrinks and expands a lot, while the composite part doesn't. And that puts a lot of stress on the glue between them. So that becomes another critical point to consider. Number 6 is that whenever you have failure in composite, and we're talking about the structure, let's say the fuselage or you have the wing, there are not just one type of failure modes. There are typically different failure modes. Let's say delamination goes in one direction, fiber fails in another direction, so on and so forth. And these are typically competing. And that makes it extremely unpredictable. So if you apply the load in one direction, a composite wing might fail in a specific way. And then if you change the condition of the load, it might fail in a different way that you didn't anticipate. And this becomes quite challenging if you want to design a structure with these materials and you're not 100% sure how this material is going to fail. How are you going to ensure that you have proper safety factor at the end for these structures? So something else to consider when designing with these materials. 7, environmental factors have a huge impact on the performance of these materials. And here's 2 images and 2 videos where basically one shows a material where a mass is placed on it, and then it can resist, has a high bending stiffness. The second one is the same material where you increase the temperature and go above the glass transition temperature of the thermoset material, which is in the composite. And this becomes, this makes the material quite rubbery with much lower stiffness. So it deforms a lot more. So understanding the effect of temperature on these materials is very important. Understanding the effect of humidity on these materials is very important. And this is one of the sample test results published by FAA. If you take a base material, let's say you're measuring one material property. So y-axis is material properties. On the x-axis, you have different conditions for testing the material. So you have cold temperature, room temperature, let's say a bit higher temperature applications of like a bit higher than room temperature, and then maximum operating limits, MOL temperature. So when the structure goes into an extremely hot environment, what's the maximum temperature that it might experience? As you start increasing the temperature, the properties are dropping. And as you get closer to some critical values, this drop becomes quite significant. So glass transition temperature is where this actually drop becomes almost vertical. And then the drop is very different if you're testing a dry sample versus if you're trying a sample that has been in a humid environment. So the wet samples would have very different drop in material properties if you're increasing temperature. So to understand this dynamics, you end up testing the materials at different environmental conditions, at wet conditions, at hot and wet conditions, at cold conditions, at room temperature conditions. So you have to come up with a matrix of temperature and humidity and expose the material to those conditions before testing it. Number 8, it's quite challenging for us to do analysis on composite strength and composite failure. Here's some examples, which we're going to discuss this later on. This would be the last lecture of the course about crashworthiness. Let's say you have a composite fuselage, and to certify this, to show that this can actually handle the case of an impact, you drop the fuselage from a certain height, and then you have to be able to analyze the failure. For some specific cases, you might be able to develop simulation capability, but in general, it's very challenging for us to simulate the behavior of a new structure that we haven't studied before, to simulate the behavior of a new material that we haven't studied before. So you end up doing a lot of tests to make sure that you can validate, you can verify these simulations. Number 9 is that many of the let's say, intellectual properties involved in composites, analysis, design, how to fabricate, how to do repair. Many of these technologies are, let's say, non-standard technologies. So it's not like they're standard, they're available out there for everyone. They are developed with significant investment from large companies like Boeing. So there's significant investments, and therefore you have to have a very trained workforce to be able to implement those technologies. Typically, they haven't been trained when they enter a large company. So you invest a lot in developing these technologies and having a trained workforce. So hiring and training people for this non-standard technologies becomes quite critical. Even, and it's number 10 that FAA conclude this list, that even for the most experienced people, there's always something new to learn, because there's always new technologies that are coming in. Here's a picture of an automated fire placement machine, which makes the layup process into an automated process. So there is a huge learning curve to go from how to do this process by hand versus how to do it by robots. So even the most experienced people have to go through this learning curve and learn a new technology. Okay, so you might disagree with that list, or you might have other opinions of what should be added to that list. But I think it's a good starting point to understand the main differences of composites and other types of materials like metals in aerospace. Okay, so some of the challenges of compositing, and this is a list that has been published by FAA. There are 5 challenges that we're going to discuss, and some of them may be a bit more details. One is dollar economics of using composites. It's very different, as you're going to see in a second. Lack of standards in general. So if you look at metals, and we'll discuss this in a bit more. If you look at metals versus composites, we have standards on how to process metals, how to weld metals, how to inspect metals. But composite is a very different word. Lack of trained composite resources, lack of evolving composite technologies, very fast new technologies coming every year, and you have to learn new things. So it's a very fast moving domain. And then many times you have to make decisions on a certain, let's say, part or a certain design, or management typically has to make decisions of, for example, where to make this factory, how to do this, which direction we have to go in terms of what type of aircraft we have to manufacture. Many decisions have to be made, and sometimes the decisions are made based on cost and other considerations, competition, for example, rather than the underlying physics and the engineering aspects of it. So that sometimes hurts the end goal, and there are many examples of that. So let's go through this with more details. I'm going to start with cost. There's high non-recurring costs when we're talking about composites. So what are recurring and non-recurring costs? So you're paying for material every time you're making a part. You're paying for labor. Every time you're making part, you have to do inspection to make sure if it's okay, the defects are low. So you do ultrasonic inspection, for example. These are all costs. So these are recurring costs that you have to pay. Specifically, for example, inspection is something that's a composite cost for inspection is typically higher compared to metals. And that's because of that connection between you go from raw material all the way to the final structure. Non-recurring costs are the costs that you have to pay upfront, but you need to do that to start the whole, let's say, process. So you have to pay a huge cost for capital equipment. You have to buy an autoclave, and these are tens of millions of dollars. You do design, you pay a lot of money for design, and you do it once, and then you have a design for, let's say, Boeing 787. The tooling, so you have to pay a lot of money to buy tools that can be used to make composite parts. So those are extremely expensive, but you have to pay it once, and then you're using it for every production. So this non-recurring cost is so high that it becomes a point of decision making upfront because a manager basically has to sign off on all of those non-recurring costs. So the moment you decide to go into a specific design upfront, you might put in 70%, 80% of the entire cost of that program. So it's a big decision to make upfront. Some of those are not even uh, intuitive. They're non-intuitive. For example, when you talk about the cost of tooling, it might be an extremely high cost upfront, which you might not even consider when you're putting a program together. So equipment and tooling, um, high capital cost upfront, and that becomes something again that you pay once, but you have to make the decision. Do I need to make this tools? What geometry of tools? So there's no room for mistakes when you're going through these processes up front. So what does this mean that there is high non-recurring costs? So many of these companies like Boeing or Airbus, they have to go through this process every time they have a new program. So they develop expertise that these expertise are and technologies and expertise that these are not standard intellectual properties. And so typically they're reluctant to share the technology that they have developed with public domain. Um, it's a market advantage for them. If they know a technology and they can implement it internally, they can compete. And they have paid a huge cost upfront to develop a design, to develop a manufacturing process. Why would any company share that publicly? So it's good in one way that that company can compete, but when it comes to trained workforce, it becomes a huge challenge. So when you graduate from a university, typically you don't have background in any of these technologies, hence the need for having many of these type of certification courses. If you look at the standard documents that are out there, there are some standard documents like ASTM documents. CMH17 Composite Manual Handbook is one of those handbooks, but these are typically very introductory. They're very limited. Um, the actual knowledge is typically resides within large companies like Boeing, Airbus, Lockheed Martin, and so on and so forth. Um, this is something interesting, like an example of how you develop a manufacturing process. And you might have seen this if you have taken my other course. So when Boeing was making the Boeing 787, the decision was made to divide the entire design into small bite pieces, if you will, for example. So the front of the fuselage, section 41, is a small piece. The wing is another piece. So you have many different pieces. And they put this for bidding for different companies. And different companies, they develop technologies. They demonstrate that they can actually build these pieces, and they won a contract. And Boeing was making some of these pieces, but not every piece in the Boeing 787. And so the assembly is done by Boeing. But you can see that every piece is different. So the technology and the manufacturing process, even the material that has to be used to make those pieces are different. It becomes a risk for one company to develop all of these technologies because all of those non-recurring costs, they have to pay for that non-recurring costs, and every piece is different. So here, to de-risk the process, Boeing made the decisions to create this global supply chain. So to share the risk with other companies, such as Mitsubishi, who they developed a process to fabricate the composite wing for 787. So what is the process to show that, okay, I have a design and the design is safe, it has a specific safety factor, and it can get stamp of approval. So we call that a certification process. So basically to achieve aviation safety, the certification agencies, the certifying agencies like FAA, they have to look at your design, they have to stamp your production process. You have to show that you have a maintenance and repair process. That if something happens, this is the step-by-step process that you're going to implement, and how you're going to operate this fleet. So every aspect of the process has to be well developed, has to be certified and validated by certification agencies such as FAA. Part of this process is to create documents, and we're going to talk about some of these documents, and this is where I'm going to introduce you to some terminologies. You need to develop, as a company, you need to develop a material specification, which we're going to discuss that in details. Basically, it's a document that lists all the properties that the material has to meet, physical, mechanical, chemical, and also in details lays down the way you can test the material for those properties. So that document is quite key when you are developing a new design. Process specification is a similar type of document that in details describes how to manufacture a part, what temperature you need, what temperature cycle you need, how many thermocouples you have to place in the part, how do you vacuum bag it, how do you put it inside an autoclave. After it's done, how do you do testing, inspection, what type of mechanical test you have to do to show that the part has been processed properly. So a process specification document is also quite critical in a certification process. Another important thing which we're going to discuss this week is statistical design allowables. And that is basically to say that I have tested the material in many different conditions, and I have high confidence that this is the response, let's say, of a tensile behavior of the material. It's limited between this lower bound and upper bounds, and I have high confidence in this statement. So those are called statistical design allowables. I'm going to go through this one by one, and you're going to understand it's a lot better. So we're going to discuss material specification. We're going to discuss process specification. And in summary, again, material specification or material specs defines all the properties, attributes of the material, and what are the qualification tests that you have to do to show that it meets those limits. Process specification defines how to do the process, how to control the process, and what type of tests you have to do to show that you have gone through that process successfully. So let's look at some of these. Before doing that, I'm going to talk about this statistical properties as well, and the way we are doing certification. So in week 4 of the course, we're going to discuss this slide in a lot more detail. So the process of certification is that I mentioned this last week. You have a building block pyramid where you do test and simulation at every level of the pyramid. You start at the base of the pyramid where you do a lot of coupon level testing and simulation. Then you go higher up and you add more complexity to your design, and you do less test because test becomes expensive, and you go all the way to one final piece, which could be like, say, the wing of an aircraft, and you show that you have a safety factor of 1.5. We're going to discuss the base of this building pyramid now, And that's the base that you develop many of these statistical properties. We call them design allowables. Design allowables are basically the statistical value for all of these properties. For example, what is the tensile strength of the material? This is the curve that describes the tensile strength of the material. And I have tested it for different materials, different layups, different geometry of the coupons, different environmental conditions, for example, at hot, wet conditions, at cold conditions. And for all of those, I have this curve, a statistical curve. And we're calling them design allowables. So it could be something like this, and this is the way FAA defines this. Basically, it says to establish material allowables, those are statistical values. You must do a lot of tests to account for two main things, raw material variability and fabrication process variability. For example, you might end up doing 18 tests, and these are some of the number of tests suggested by FAA to establish mechanical properties for some secondary components in an aircraft. And the way you're doing that is that you are making flat panels, let's say. Each time you're making two flat panels. So let's say you're making two flat panels inside an autoclave. You run the autoclave 3 times, so there are 3 batches. Every time there are new panels you're making. So that brings in the variability of your layup and the placement in the autoclave. So you're including that. And from every panel, you cut, let's say, 3 coupons. So that brings in the variability of the material. So you will end up doing 18 tests, 6 times 3 from the 6 panels. And then you plot the results, and let's say you're just measuring tensile strength. You plot the results. The value which is associated with the lowest 10th percentile is called B basis design property, or B basis allowable. The value that is associated with the first percentile, we call it A basis. So when you're talking about A basis, B basis, these are basically the lowest percentile, the lowest 10th percentile that represents the statistical properties of the material. And again, 2 things are considered there, material variability and process variability. This is also a document from FAA that describes in more detail. If you're interested to learn more, you can take a look at that. Here's, for example, if you do all of those tests, you have to come up with a document to say, I have done this test. This is what I'm reporting in terms of statistical properties. This is a sample document. It says that the material which was tested is an Hexcel 8552 IM7. IM7 is the type of carbon fiber. 8552 is a type of epoxy. You have tested it in unnotched compression. So it's just flat rectangular coupons, and you've tested it in compression. This is the layup that you have used in all of these tests. You've measured the density, you've measured the resin contents and fiber contents. The way you have done the test follows the ASTM D6641. You have measured the thickness, and this is a normalized thickness. And this is the way you're reporting it. You have one column for room temperature dry condition, and you have one column for elevated temperature wet condition. So room temperature dry is 70 F dry. The other one is 250 F, and the sample has been conditioned at 160 F to 85% humidity before doing the test. And you're reporting strength, modulus, and Poisson ratio. For example, for strength, you're saying I have done 16 tests as room temperature condition, 27 tests and elevated temperature wet condition. I'm reporting the mean value of the strength, normalized and measured value. I'm reporting minimum value I measured, maximum value I measured, and coefficient of variation, which is the standard deviation divided by the average. So you report all of this as statistical value so that they can be used in your design beyond this. So we call this basically your design variables. Okay, so what is material equivalency? Sometimes if your you have done all of these tests before, and you're slightly changing your material, you're slightly changing your facility. For example, you have a new autoclave. You're slightly changing the way you're doing vacuum bagging. So your changes, you don't do a drastic change, but still there are changes, minor changes. FAA might allow you to do a subset of tests to show that there's equivalency between them. So we call this equivalency. So let's say for the original material, original process, you've done 18 tests. You define a subset of those tests that you're going to do to show that these two materials are the same. So you might end up doing 8 tests. So this is only, again, for minor changes. Another definition that we're going to have, which one of the case studies we're going to discuss is related to this, is what do we call a controlled material property, or a controlled material, or like a mature material. So we're going to talk about that. Let's say you're receiving material from a vendor, and you're measuring every time there is a new roll comes in. You make these panels, and you cut the samples, and you measure tensile strengths, let's say. So that's tensile strengths. And you plot them in this curve. So this is the first time you did the test. So there's a variation of that. And then you look at the number of batches. Every time there is a new roll comes in, you do a new sets of panels and new sets of coupons. So all of these vertical lines, vertical dots, represents like your the results of the test and variation of the test results. If you look at this, and if you plot a line, there's a yellow line that represents the lowest first percentile. You can see that all of these tests are more or less sits above, all of them are sitting above that. So this is what we call a controlled material. Its first percentile and its 10th percentile, let's say, or its minimum values, they are constant, they're not changing. If it goes ups and down, it's not a mature material. It seems that either the material is changing or the process is changing, something is changing, and that's not what you want. So you do this test to show that the material is mature and material properties are not changing. So even though you have established all of these and you have a factory and you're making parts for years, every often you have to repeat this test to make sure that the incoming raw material doesn't change and your process is still the same as before. Let's say you do a test like that for a specific material incoming to the factory, and you see this, that after a while, the material properties are dropping. This is not what we call a stable material. So the material properties are changing in time and it's dropping. So if you're doing the design based on the first batches that you have bought from the vendor, obviously in time it's decreasing. It's very dangerous because what you will end up in an actual part is much weaker than what you actually anticipated at the beginning. So you have to do these tests to make sure the material is stable. But sometimes you do a test and like this, and you see that the strength goes up rather than going down. Is it good? Is it bad? I mean, the lowest percentile doesn't changes. Let's say that the lowest 10 percentile also doesn't changes, but like let's say the average of the data is changing. You can kind of see that the average is going up. So it's like the material becomes stronger as time goes by. This is also not a stable material. It might seem a good thing that the material becomes stronger as time goes by, but actually it's a very bad outcome. The reason is that goes back to one of the factors I mentioned about composites. Composites fail typically in an unpredictable manner. If let's say you are making a component stronger than your design, all of a sudden the dynamic between the competition between failure mechanism changes. That part could have been a sacrificial part to make sure the failure goes in a specific direction. All of a sudden it's a stronger design. So the failure goes into a direction that you didn't anticipate. So it's going to hurt your design. It will have lower safety at the end. So you should not accept this as a stable material. So typically there is a period of time that you're doing trial tests and you're developing your process. The material is still going through changes. So it's a maturity process. So let's say properties A and B and C are all changing. But at some point, when you go to production, you want to make sure everything is constant after that. So this basically shows that. So it shows that the maturity increases and then everything becomes constant and it's a mature material. Okay, so now let's talk about the actual specification. So the actual document, which is material specification and process specifications, these documents are typically not open to public. These are part of those documents that the company has developed for a specific program. There's lots of intellectual properties attached to them, so they're not publicly shared. But we have understanding of what type of information should be included in these documents. And some of these are published by FAA to show that what has to be included. So in the process specification, sorry, in the material specification documents, you have to have how to identify the material, Excel 8552 IM7 identification. The references, definitions, what are the material requirements in terms of physical, chemical, and mechanical? For example, tensile strengths under mechanical should be this much. What are the test methods associated with all of those properties? And how do you qualify those material properties? For example, you will do mechanical test, tensile test, and you do 5 tests, and you show that you have minimum this much strength. These are all specified here in the material specification. It has information about when you have an incoming material, how to make sure its quality, how do you control the manufacturing, and if there's supplier and purchasing variation, what are the testing requirements to make sure that the materials are the same as before. It has information about how to package them, how to ship the materials, how to store the material. And again, these are specific to one material, let's say for one program, and we don't have access to, let's say, Boeing 787 um, specification material. But I will share with you the sample document that has been shared by FAA. Let's say under the mechanical testing, it identifies what properties have to be tested, at what condition, and how many tests and following what method. For example, it might says test the 0 degree along the fibers, tensile properties and modulus at room temperature using ASTM D3039 and do at least 5 repeats, and so on and so forth. Compression, short beam strength, whatever you have. So this is sample information that has to be included in material specification. This is related to one of the cases that is this weekend, and you're going to discuss this with Christos on Canvas. And that is, many assume that you are purchasing a material under given material specifications. So you as an engineer, you're given material specification documents, and you're buying the materials from, let's say, 3 vendors, and you have material A and material B and material C, or they're coming from the same vendor, and they're all satisfying specifications. But are these the same materials or not? Do they have the same design values, design allowables or not? And typically the answer is not. They're not the same. And let's show an example when they're not the same. Let's say that you have bought 3 different materials, material A, material B, and material C, and you're looking at the strengths of the materials. All of them are stable, mature materials, so their properties are not changing. They're all satisfying the minimum value for strength, and let's say the minimum average or the 10th percentile strength. They're all showing strengths above that. But if you look at the absolute average, material C is a bit stronger than material B, is a bit stronger than material A. So material properties are a bit different, even though they're all satisfying the minimum requirements. So all of these materials are satisfying process specs with respect to minimum strength values. But if you end up doing design with these materials, they're obviously not the same material. And again, it's not sufficient to say material C is stronger than B and B is stronger than A. Therefore, it's okay to have the same sets of properties for all of them. As I mentioned, you have competing failure mechanism composites, and it's a very dangerous path to have a material which is stronger than other materials. So it's not a good approach to assume that since they all satisfy minimum requirements from process specification, therefore they're the same material. The correct way is to do something like this, to say that even though they are the same material, even though they are all mature materials, let's say they're coming from different vendors, their minimum values are a bit different. Therefore, you will have different design allowables for each material. Even though they're all satisfying process specs, even though they're all under the name, the same material, they will have the same statistical design value at the end of the day. Okay, so a process specification documents might have several sections, and this is one example of section 1 to 5, what you have to include. For example, requirements when you are doing the process, what material is required, what equipment is required, facility, tooling, how do you do inspection, how do you do your thermocouple. So there's a lot of details on how to make sure the temperature curves are recorded and they're consistent. What is the pressure setting inside the autoclave when you're making the part? And again, just like the material specification, process spec documents are also not available typically in public domain. There are some sample documents for some non-sensitive materials, but typically the materials that are used, for example, in Boeing 787, you don't have access to process specs of those materials in public domain. So let's see some example of what's typically identified. When you are doing processing of composites, you end up using a lot of consumables. So here are some examples. You're making parts, you're placing prepregs onto a tool, and then you vacuum bag the entire process. And you see the vacuum bag and you see the yellow tacky tape that is used to create a vacuum envelope. So these are consumables, and we've called them non-flyaway materials. So every time you're manufacturing a part, you have to use this consumable, and then you throw them away. Do you need to have information for these consumables in your process specs? And the answer is absolutely yes. You have to identify in this program, we're going to use this specific vacuum bag with these conditions, this tacky tape with these conditions, and you have to lay that down quite clearly. The reason is that, let's say you're doing manufacturing, and then this tacky tape that you have here, this yellow tape, can only hold vacuum, let's say up to 100 C degree, but then you are manufacturing the part at 180 C. So at that temperature, it's going to lose the vacuum and it's not going to hold the vacuum anymore. So if you don't specify that in the process spec documents, and if another engineer takes the document and starts going through that process, it creates trouble. The vacuum bag, the breather that goes under the vacuum bag, there's lots of consumables. And each of those, the properties of those has to be identified clearly. So it's not just the material, but also non-flyaway material, the consumable that you have to define their information in the process spec document. When it comes to the prepreg itself, let's say the optical processing, you have to identify the temperature cycle and the pressure cycle that the material has to experience inside the autoclave. And these are needed to make sure the defects in the material at the end of the day are minimized. If you don't follow this specific recipe, then the end result has low properties. So think about this as like a cooking recipe, and you have to follow this to the letter. So you have to exactly follow this temperature cycle and this pressure cycle. Not only that, you have to place thermocouples in this specific areas, for example, as specified in the process specs, and the number of required thermocouples to show that you have followed the temperature cycle. These are all, again, specified in the process spec documents. finally, when it goes to, it's not just the layup and cure and assembly, all of those things. At the end of the day, you have to have information of how to inspect this, how to, if you have bonded joints, what are the details of those, how to do the inspection of those. But ultrasonic inspection, for example, could be part of this process specs or could be a different document. Some of the testing that you have to do at the end of the day, for example, after the manufacturing is done, we're going to do these 5 types of tests to show that the final properties are satisfying our properties. Those are also could be identified inside the process spec. Okay, so this is the last slide for this week. And I think the aim, I'm going to go back, a couple of main fundamental issues. There is a document which is material specification document. There's another document which is process specification documents. And both of these are developed with some high details to ensure that every aspects of the limitations and challenges of the materials are addressed, and you have a very good understanding of a statistical value of the material. And you can ensure consistency at the end. The material remains mature, your process remains mature, and not only what maturity means, but you understand what testing you have to do in time to show that everything is stable. So I think you're now ready to answer the 2 case studies, which we're gonna post on Tuesday on Canvas. And again, you have to have 3 participation for every week. Again, I apologize that it's a pre-recorded lecture. Please contact me if there is any questions or if you have any difficulties understanding any of these topics. I'll see you after I come back from my trip. Bye.